Okay. Hello, my name is Dana, and I'm an electrical engineering student at U of T. I'll be going into my 4th year at U of T this coming September. My research supervisor is Professor Sean Hum in the Electromagnetics group under the Department of Electrical and Computer Engineering. I'm assisting Elham, who is a postdoctoral fellow with this project. We are continuing the work done by a previous master's student, Gerstenbrand. I will be presenting today about leaky wave apertures for antenna applications. This is the agenda for my talk today. I will first be giving you some background information and then talking about the purpose of this project. I will then show you the method and the results, as well as the progress made so far and the next steps. Satellites play a major part in assisting those who live in the remote Canadian Arctic. For example, the RadarSat satellite facilities facilitates ecosystem monitoring and as well as disaster management. Satellites even help to improve remote access to healthcare and locate ships or other marine traffic all the way from space. Not only this, but communication with satellites are a key part of every Canadian's life, supporting television, cell phone service, and the internet as well. The impact satellites have on society today is incredibly widespread and very important. Ensuring that this communication is efficient and robust is important to maintaining the high quality and reliable service that many people depend on. Highly directive and reconfigurable antennas can help in establishing this efficient and robust communication network. Low Earth orbit satellites can travel over 8 kilometers per second and can complete a full orbit within about 90 minutes. Upon establishing a communication link with an orbiting satellite, ground space station antennas must physically move to track the path of these fast-moving satellites. This movement is demanding on the mechanical parts of the antenna and also consumes a lot of time. This mechanical fatigue significantly lowers the lifespan of the antenna. Beam forming occurs when a beam of energy is created from phased antenna arrays. An antenna array is a set of many antennae that work together to act as one single unit. Phased arrays can actually control the shape and the direction of these lobes of energy. This is because the various unit cells within the array can create the beam by constructing and interfering with one another. Electronic beam steering takes this one step further. It consists of dynamically changing the beam by increasing or decreasing the phase. Since it is electronic, no physical components of the antenna need to change or move in any way. It can actually change the direction of the beam without any movement. This can be achieved using antenna arrays, which steer the beam by changing the different phases and time delays of the array, making the communication with satellites a lot more efficient. Many ground base stations actually manage more than one satellite in what is known as a satellite constellation. And these base stations need to dynamically track multiple orbiting satellites and change the links amongst them, which can be achieved with this electronic beam steering. The purpose of this project is to develop an antenna array that will perform electronic beam steering. A reconfigurable leaky wave array has been designed by Gerstenbrand to combine the reconfigurable abilities of a transmit array and the directive ability of a leaky wave antenna. You can see a sample antenna array layout in the slide. The leaky wave array design takes advantage of the fact that energy is emitted, or leaked, in periodic intervals from the guided structure as it travels along. The diagonal arrows in the diagram give you an idea of the decreasing radiated energy as the wave travels along. This concept is combined with transmit array elements, which are typically called unit cells, that are excited by the wave. As the wave travels from the feed and propagates to all the surrounding cells, it accumulates a phase. And this phase is reconfigured by decoupling and is able to allow for continuous beam steering at any arbitrary angle. The unit cell is the key to the entire design. The array is essentially populated with multiple unit cells in order to achieve beam steering. The unit cell has 2 requirements: correct leakage characteristics and reconfigurability. For one, the unit cell must leak the correct amount of power. If the unit cell leaks too much, there would be reduced gain, and if it leaks too little, there would be leftover power once the wave finishes propagating. The unit cell must be designed to leak the perfect amount of power. Secondly, the unit cell should give over 360 degrees of phase range. This is to ensure that it can allow for beam scanning and is achieved by using different strip line lengths, which are seen in the images. There are three main layers of the unit cell: the input slot layer, the strip line layer, and the output slot layer. The inner layer determines how much leakage the unit cell has. The length of the dog bone slot controls this leakage. To determine the optimal length of the slot, simulations were performed by Gerstenmann to find the ideal length based on the layer's response in a periodic environment. Each unit cell differs in the length of their strip lines. The differing lengths correspond to varying phase delays, and hence will make each unit cell reconfigurable. A longer strip line would increase the delay, and therefore the phase as well. The output layer is similar in design to the input layer. The difference here is that the dog bone slot is rotated 90 degrees in order to reduce coupling amongst the input and the output. This project is supported by an industry sponsor, and several design specs were received from them. The array will have an operating frequency of 19.5 GHz and will be able to steer a sharp pencil beam of 25 dBi gain to any angle. You can see on the slide the radiation pattern and what looks like a sharp lobe at 0 degrees. This type of radiation pattern is expected for a pencil beam, as you can see from this plot that the majority of the energy is directed at this angle. The sponsor had also requested an effective aperture diameter of 400 meters. An antenna with a large effective area is able to give a large gain and hence can be very directive. This design was originally done as a proof of concept, and in the future it can be modified and scaled to whatever the sponsor prefers. Thorough full-wave simulations in HFSS, which is a finite element method solver, will be conducted beforehand. Recent progress was made to import the unit cells into HFSS in the layout formation, and the previously plotted phase responses were verified using MATLAB. 24 unit cells with differing strip line lengths were realized, corresponding to the different phase states, as shown in this plot. Modifications from the previous design were made after identifying the exact size of the exclusion zone, which is an area of the design that should not be populated by unit cells due to this nonlinear radial phase constant within this radius. The previous layout scripts were changed to import all parts of the unit cell and translate them to the correct placement in the array. You can see in the short video of the script running in HFSS for the first ring in the array. Once this layout process is complete, we will soon move on to running the full simulations and test of the layout in HFSS. We will be pursuing prototypes of the array layout for 3 different pencil beam angles, and the cavity that encases the array will be designed and fabricated. We plan to look for people to manufacture the designs for us so that in-lab testing can begin of the prototypes. The cavity will hold the PCB stack in place, and it can be fastened by using the bolt holes that will be drilled into the cavity. The edge of the cavity actually creates a short circuit, and the feed line will enter the cavity through a hole at the bottom and will excite this waveguide. I've recently modeled the proposed cavity design using AutoCAD and will be contacting companies to have it machined. The finished array will be tested in the antenna laboratory at U of T using a planar scanner. The scanner is used to measure the far-field radiation pattern. Thank you so much for your attention and for listening to my presentation. I'll now open up the floor to questions.
Right. I will go first again. I've got 2 questions. My first one is from a very primitive knowledge of spacecraft. Typically, communicating with a spacecraft is a 2-way affair. So it's not just about sending a beam in the direction of the spacecraft, it's also receiving the signal from the spacecraft. Does your antenna do the receiving part as well? I mean, you just talked about transmission. How about receiving?
Yeah, that's a good question. So I guess my part of the project was more focusing on the transmission from these ground-based stations. But I think in the future, the sponsor might kind of consider this option as well and look into like doing the uplinks as well as the downlinks for the communication purposes.
Okay. The other question I had, and I don't know whether I missed it anywhere. I didn't get a sense of the scale. What were roughly the sizes of these little components that you were putting together?
Yeah, that's a good question. So the whole array is going to be 400 millimeters in diameter, but each unit cell is 7.2 millimeters in diameter.
Oh, okay. So they're tiny. Okay.
Yes. Yeah.
Thank you.
Thank you.
I'll ask a question. Great job. That was a very good presentation. I'm curious, are you aware of other existing research projects that are trying to solve the same problem using different approaches?
Yeah, I'm not too sure, but I know that like Gerstenmann, he kind of identified other projects that are capable of the electronic beam steering, but they don't use the transmit array plus leaky wave aperture design that he kind of proposed in his thesis that we are trying to design now.
Okay. And in terms of your approach or your team's approach, what do you identify or believe is the sort of chief obstacle to what, and not that there has to be one, but is there a chief obstacle that you are aware of or concerned about?
Yeah, it's probably like the directivity and just making sure like the pencil beam that I showed in the slide is as directive as possible, because the point of it being directive is so that like the radiation doesn't go off in directions that you don't want it to, and that it should kind of hit the satellite as much as possible. So just getting this to be like as directive as possible is one of the major obstacles.
Okay, thank you.
Thank you.
Just, I'll jump in with another question here. It strikes me that this method of transmission must be more or less energy efficient than using a larger array that you're physically pointing. So you're trading off increased power for transmission power for not having to do the physical moving of the antenna. So I mean, it's probably a good trade-off, but can you give me a sense of how much more transmission power must be required to do things this way?
Yeah, that's a good question.
Or you can tell me I'm completely wrong too. So.
No, I know that, so in terms of electrical power, this one definitely uses more, but in terms of mechanical power, it's 0. But I've been more focusing on the layout aspect of this, so I'm not entirely sure like what the finished layout, how much power we'll use, just because we haven't like completed it yet. We're still kind of in the process. But yeah, in terms of the trade-offs, it's more so a mechanical versus electrical power trade-off.
Okay.
Thank you.
Okay, and we're at time for Q&A, so we can move on to the next presentation.
Great, thank you for your presentation. Iwan, are you ready?
Yeah.
Great.
Could you see the PowerPoint?